Hello, pre-calculus honor students. Here we are with 12.4, parallel and perpendicular vectors, and the dot product. We're going to try and find and apply the dot product. First, let's kind of see what makes vectors parallel and what makes them perpendicular using GeoGebra. So let's say we have one vector here, and it goes from like 1, 1 to 5, 3. And that's the vector 4, 2. Okay? Now, what makes a vector parallel? Well, if I come over here and start at a different point, let's see here. Let's try and make this parallel, but maybe not the same length. Does that look parallel? Let's find out. 10, 6. Are those two parallel? Well, one way to see is to change these vectors into their polar coordinates. Nope, I didn't make them quite parallel. So let me get the same angle on this vector. Slide it down. There, now they're parallel. So those are the polar coordinates of those vectors, the magnitude and the direction. Let's change them back to their component form now, their Cartesian coordinates. And we have 4, 2, and 10, 5. What's true about those? Is there an easy way to take vector u and multiply it by something to come up with the other vector? If I take vector u and multiply it by 3, let's say, I get a longer vector. I get 12, 6. Let's multiply it by something else. How about vector u times the scalar, not 2, how about 2.5? Boom. And see how we match it? There's w, 10, 5, and there's v, 10, 5. So when the coordinates are proportional, we end up with parallel vectors. It works too if you multiply by negative vector, negative scalar too. So we could have come up with our parallel vector very quickly by just taking u, multiply by anything. Let's multiply u by, let's see, times negative 2. And sure enough, we end up with a parallel vector. This one headed in the opposite direction. It's definitely parallel. Okay? Now, perpendicular is a little trickier. For perpendicular, let's come up with some new points. Let's do a vector again. Start at negative 1, 1 here. Oopsie. Yeah, we're on vector drawn. We're making vectors. There we go. There, does that look perpendicular, folks? Well, we can check it this way. We can look at their polar coordinates again and see if we are 90 degrees out of sync. Not quite. Let's adjust this until we get them to be 90. How's that? Does that look like 90? No, it's got to be 116. I got to go this way. Oh, this could be tricky, huh? How about that? Is that perpendicular? Isn't that 90 degrees out of sync with each other? Sure enough. Now, what's true about the component form of these vectors? Let's take a look at that. The Cartesian coordinates. 4, 2, and negative 3, 6. Well, maybe you see a little trick here. They're not proportional because I can't multiply 4, 2 by something to get to 3, 6. But it's a little something called the dot product. I'm pretty sure it's in here. Dot product. dot product of u, well, let's just put it here, u comma v. Yep. But if you notice, if we multiply the 4 and the negative 3, you get negative 12, and the 2 times 6 is positive 12. There, in the essence, is how the dot product is going to tell us if the vectors are perpendicular. So here we go. Okay, so from what did we learn from GeoGebra? That if we have vectors that are parallel, they're parallel if they're scalar multiples of each other. If they are scalar multiples of each other. What makes vectors perpendicular, though, is a little trickier. Then the products of their slopes must be negative 1. Let's write this out algebraically. Scalar multiple means that v1 will equal some scalar k times v2. But now, for perpendicular vectors, how do I get their slopes? Well, let's take a look at a little chart here. Let's say we've got over 4 and up 3. That's the vector 4 comma 3. What's going to be perpendicular to this? Well, this has a slope of this has a slope of 3/4. So to get the perpendicular slope, we do the negative reciprocal. We flip it, and then we change one of their signs. So notice we're going to go back 4. So for this had a slope of 3/4. This has a slope of negative 4, 3. It corresponds to the vector 3, negative 4. 1, 2, 3, 1, 2, 3, 4. Notice we could have also done the vector negative 4, 3. 1, 2, 3, 4, up 3. No. Scalar multiple of this, sorry. Negative 3, positive 4. 1, 2, 3, 1, 2, 3, 4. There you go. So that would also be perpendicular to our original vector. So the dot product takes that idea and turns it into an equation. If v1 equals x1, y1, and v2 equals x2, y2, then the dot product of the vectors is denoted by this. We use a big dot to distinguish it from just plain old multiplication. And it's x1, x2 plus y1, y2. We saw that when we were exploring GeoGebra, that we could just multiply the x coordinates, multiply the y coordinates, and if they're equal to 0, then we get something. Now, the dot product of two vectors yields a scalar. So that's what some might call the scalar product, but it is not a scalar multiple. It's not scalar multiplication. We'll just call it the dot product. If the dot product of two vectors equals 0, then the vectors are perpendicular. Perpendicular. And there's our perpendicular symbol. So question, can the dot product equal this? The basic answer, no. This product we talked about a little bit with complex numbers. But this is a product between two vectors. So these are not equal. Does not mean the same thing. Now here's a few remarks about perpendicular vectors. They're sometimes called orthogonal vectors. It's customary to call v1 and v2 parallel when they're scalar multiples, even though the arrows may be collinear and they may actually be in the same line. You might be used to the idea of parallel meaning beside each other, but we're willing to have parallel mean in the same overlapping. The zero vector is both parallel and perpendicular vectors. Please note if I ask for a vector parallel or perpendicular to the given vector, though, don't just give me the... Okay, here we go with example 1. We have vectors u, 3, negative 6, and vector v, 4, 2, and vector w, negative 12, negative 6. And we want to find u dot v and v dot w and show that u dot v is perpendicular and v and w are parallel. So, let's start with u dot v. U dot v equals 3, negative 6, dotted with 4, 2, and you get 3 times 4 plus negative 6 times 2, 12 and negative 12, that's 0. So since u dot v equals 0, that means u is perpendicular to v. Perpendicular. Now, let's see what happens with v dot w. V dot w is equal to 4, 2, dotted with negative 12, negative 6. So that ends up being 4 times negative 12 plus 2 times negative 6. And we get negative 48 and negative 12, which is negative 60. So v dot w equals negative 60. They're not perpendicular. Does that mean they're parallel? Well, not necessarily. We have to show something else to show that they're parallel. Notice, though, that there's a scalar multiple between the two. Since v equals 4, 2, and w equals negative 12, negative 6, if you can think of a way of multiplying this by scalar to get to there. So just look at one coordinate. 4 to get to negative 12, you have to multiply by 3. Well, will that also work with 2 going to negative 6? Yes, you multiply by 3. So, since w equals, sorry, by negative 3, negative 3 times v, w is parallel to v, since they're scalar multiples of each other. Okay, here's some properties of the dot product. U dot v equals v dot u. It's commutative. U dot u will equal, now let's think about this for a second. U dot u ends up being the magnitude of u squared. Let's kind of see why on that one. How does that work out? U dot u, let's say u equals a comma b. For u dot u, you're going to have ab dot ab. So that's a times a plus b times b. That's a squared plus b squared. And the magnitude of u is the square root of a squared plus b squared. So there you go. U dot u equals the magnitude of u squared. If you do a scalar multiple, k times u dot v, you don't distribute it. You do sort of an associative property and just have the scalar multiple times one of the vectors. Now, oddly enough, the dot product does distribute over addition. So u dot, the vector addition of v and w, is u dot v plus u dot w. Okay, just a few properties there. Now, this is going to help us now in finding the angle between two vectors. It can be very tricky. So, let's say we have two vectors. We'll call them u and v. And we want to find this angle theta between them. Well, first, by vector arithmetic, v plus this vector here will equal u. So this vector will equal u minus v. So this is vector u minus vector v. Check it with the addition again. Here's vector v, here's vector u minus v. They add up to vector u. Now let's look at all the sides. Let's look at the sides of this triangle that we made. The magnitude of u is one side, and we'll call that the square root of x1 squared plus y1 squared. Let's let u equal x1, y1, so we can look at coordinates, and v equal x2, y2. Okay? That means the magnitude of vector v is going to be the square root of x2 squared plus y2 squared. Okay. And now we need the magnitude of vector u minus v, which is the square root of, since the vector from v to u here is going to be the subtraction, x1 minus x2 squared plus y1 minus y2 squared. Now it's time to break out our law of cosines. The law of cosines says this. Remember that one where you had it solved? The LOC, cosine theta, is basically the other two sides squared. So that's the magnitude of u squared plus the magnitude of v squared minus the magnitude of u minus v, the third side squared, all over twice the product of the two sides around the angle. Magnitude of u times magnitude of v. Okay? Now I've got to expand that all out. So, cosine theta equals the magnitude of u squared, which is just going to end up being getting rid of that square root. So you get x1 squared plus y1 squared, plus the magnitude of v squared, so you just get x2 squared plus y2 squared, minus the magnitude of the third side squared, so it's x minus 1, x1 minus x2 squared, plus y1 minus y2 squared. Don't forget, though, that all this is in one big quantity and it's being subtracted. All over 2 times the magnitude of u times the magnitude of v. So, cosine theta equals, I think there's a lot of stuff that's going to cancel out here, x squared plus y1 squared plus x2 squared plus y2 squared minus, and when we expand these out, it'll be x1 squared plus 2x1 x2 minus x2 squared minus y1 squared plus twice y1 y2 plus the opposite of y2 squared, all over 2 magnitude of u times magnitude of v. And look at all the stuff that cancels. It's amazing. The x1 squareds, the y1 squareds, the x2 squareds, the y2 squareds, and you're left with just cosine theta equals twice x1 x2 plus twice y1 times y2 all over twice the magnitude of u times the magnitude of v. So the cosine theta, take out the 2's, x1 times x2 plus y1 times y2 over the magnitude of u times the magnitude of v. Well, that's just the dot product. U dot v over the magnitude of u times the magnitude of v. Well, that's a cool result then. In fact, there's 2 ways to write this result then. And that is, if you're trying to find an unknown angle, use this idea. The cosine of the angle between 2 vectors is the dot product of the vectors divided by the product of their magnitudes. Or you can also redefine how you do a dot product. The dot product of 2 vectors is the product of their magnitudes times the cosine of the angle between them. So here's example 2. Find to the nearest degree the measure of angle theta, the angle between the vectors 1, 2, and negative 3, 1. Let's get this back up again. So we want to find this angle between 1, 2, over 1 up 2, and back 3, up 1. Looks like more than 90 degrees. Let's see what we can come up with here. So the cosine of theta will equal the dot product of 1, 2, dotted with negative 3, 1, all over the square root of 1 squared plus 2 squared times the square root of negative 3 squared plus 1 squared. That's their magnitudes. So the dot product is negative 3 plus 2 over the square root of 5 on the bottom here and the square root of 10. So we get negative 1 over the square root of 50 which is about negative 0.1414. And then we can use inverse cosine of negative 0.1414 to get approximately 98 degrees. 98 degrees between those two. Yeah, we thought it was a little more than 90. Now, slightly different problem in triangle PQR. We've got P is 2, 1. Q is 4, 7. And R is negative 2, 4. Find the measure of angle P, that's down here then. So there's our theta, to the nearest tenth of a degree. So what we need though is these two vectors on either side. PQ, this is one nice thing about the graph paper is you can just kind of count over. You're going 1 over 2, up 1, 2, 3, 4, 5, 6. PQ is 2, 6. PR is backing up 1, 2, 3, 4, and going up 3. Negative 4, 3. Now, if you didn't have the graph paper handy, you could still find PQ, vector PQ, by doing Q minus P. That is 4, 7 minus 2, 1. So you get 2, 6. And vector PR is R minus P. So that's negative 2, 4 minus 2, 1, and you get negative 4, 3, as we said over here. Okay, now let's do our rule to find out what the angle is between them. So the cosine of theta is going to be the dot product of PQ with PR over the product of their magnitudes. So cosine theta equals 2, 6 dotted with negative 4, 3 all over. The magnitude of PQ is the square root of 2 squared plus 6 squared. The magnitude of PR is the square root of negative 4 squared plus 3 squared. So up on top, the dot product ends up being negative 8 plus 9, 18, negative 8 plus 18 all over the square root of 24 and 4 is 40. So we get 10, square root of 40 is 2 square roots of 10 times 5, and you end up with 1 over the square root of 10. And do the inverse cosine of that, 0.316227, and you get our answer of about 71.6 degrees. And that checks out. So, flange out.